Good morning. Good morning. Hello, everybody. It's good to see you. Welcome here. Welcome here. All right. Just making some paint stuff so we can speed through the first 20 minutes of class or so. English. So we can speed through the first 20 minutes of class or so today. If you can't tell by the title, today's our last day. It's the last day you get to see my face. The last day you have to come to this stream. And then as of tomorrow, and I guess Tuesday for some people, hopefully the last time you'll ever work on CS202 stuff. Most of you are doing very well in the class, so I think we have sort of a positive outcome, hopefully. Yes, I'm so sad to see all of you go, but I'm happy that we're going to be moving forward and that you guys will be better computer scientists. So, yeah, let's just talk a few notes for just a moment. Test is tomorrow, all right? I'm aware that we're working on a lot of stuff right now, so I'm going to try to keep the test straightforward. I'm not going to try to trick you too much, but it will be, kind of like the first midterm test, all right? You're going to get a whole hodgepodge of questions. I'm going to ask you for definitions. I'm going to ask you for little code bits. There will be multiple choice, and then there will be a little program at the end. All right. You need Lockdown Browser, like I said, and the test will start tomorrow at 11:15. That's when it will open. I'll give you 5 extra minutes there at the morning if you want. Starts at 11:15, 5 minutes earlier. And I will be online during the exam if you need to ask me questions. I can't help you answer them, but if you're convinced that there's some weird thing on that test, you can ask me. Or if you'd prefer, you can save it until the end. Kind of write down the question number so you can take as much time as you need for the test, and then afterwards send me a message and be like, hey, this question confused me. Are you sure it's right? And then if it happens to be wrong, I will go back through all your grades and make sure that it doesn't ruin anything. All right? So yeah, same protocol for the test tomorrow. Be sure that you are online and taking it, please. That's that. Tomorrow, assignment 8 is due. And then on Tuesday, assignment 9 is due. I know some of you have already finished assignment 9. If you didn't see my little announcement that I posted this morning, assignment 9 has a little bit of a random output. And that is, I'm letting you shuffle the cards any way you want. And so there's no way that you can possibly match my output on CodeGrade unless you typed up my code exactly the same way. It would also indicate that every single person would have to do the extra credit, which I'm not requiring. So I will be manually grading those assignments starting maybe not Tuesday. I said that assignment 9 is due on the 12th. That's Monday. So Tuesday, I'll be manually grading your assignments. So excuse me, assignment 9 is due on Monday, the 12th. I'll be grading those on Tuesday, and then you'll have your grades by Tuesday. All right, so you just have to go to Web Campus and submit your 2 card files. That's it. All right, I'll be available pretty much all weekend, so you can send me a message. I'll still help you even though the class will be over. So don't be shy. So that's all said and done unless you have any questions. We need to get started on stacks and queues. We only have a little bit of notes for this. So we're going to take our notes. I'm going to show you how they work on the whiteboard, and then we're moving on to review. All right, we're not going to do any coding today for the stack and queue. I will provide you with CPP files. Sort of today and tomorrow on Web Campus, I'll upload exception handling stuff for your records if you want. I'll upload stack and queue stuff for your records if you want. I might upload a doubly linked list if you'd like to keep that. And I'll upload Terminal Minecraft for those of you who wanted to see that program. All right, so I'll kind of give you a little bit more stuff. Even though we didn't explicitly cover it in class, you'll have it for the future. All right, so be on the lookout for that. Yes, Terminal Minecraft is epic. I guess you could call it Terraria too for those of you who are being politically correct, but no worries. All right, so stacks and queues. Let's go ahead and open up these notes. Does anyone know another word for queue? If you've ever been to England, they say some words differently there, and they use the word queue. Do you know what that means? I mean, for those of you who play like League of Legends and stuff, you'll queue up. What's the another word for this that we use in America? What do we call this? What's a queue? Chowder's right. It's a line. It's a line. It's a line. Queues are lines. If you ever go to England and you go to the McDonald's or whatever, you get in the queue. That's what they say. You get in the queue. So that's what that is. And so stacks and queues are very similar. All right. They're just lines. They're kind of different types of lines. And when you get into CS 218, you're going to learn all about the stack. DMV, yeah. You queue up at the DMV. So when you get to 218, 302, all that good stuff, you're going to be talking about stacks all the time. All the time. Stacks and queues are very important data structures. For computer science, all right? You're going to hear about them forever. They are arrays. They're kind of dynamic arrays where elements are being inserted and removed all the time. All right, just like a line. The person up front gets served, they leave. Someone in the back inserts themselves into the line, and then they're waiting. So there's people being removed from the line, there's people going into the line, all right? And so this can be done with a bunch of stuff. You can use pointers if you want. You can use linked lists. Linked lists probably would be more preferred, etc. All right, as long as it's some kind of dynamic memory. So there's only two main functions that we care about in stacks and queues. There's only two main functions, and you've already kind of seen them before, all right? And this is where it comes from. So there's two main functions. So the first thing we have is push, all right? Now I try to use this a lot in this class. So, you know, whenever we did the dynamic array or the string classes, I didn't call the function insert, I called it pushback. And the reason I did that was not only because vectors call it that as well, but when it comes to stacks, when you're inserting something to the stack, you call it a push. So the one main function here is called push. And I would say in a queue, you could call it push if you want, but in a queue they might call it enqueue. And it takes some item and it puts it in the list, all right? So you might hear that term, push and enqueue. And so this inserts the item. And it usually has a void data type, right? Usually has a void data type. Now pop, I don't know if you've heard this one before. In a queue, that one would be called a dequeue. There's my thing here. Now I should probably get my quotes right here, otherwise it's going to look goofy. And this one removes stuff from the stacks and queues, all right? That's all it does. I'm going to call it the top item from the list. This one will have the same type as the element. So returns whatever type the list is. All right, so if it's a list of ints, it's going to be int pop. If it's a list of strings, it's going to be string pop. All right. So that is what type pop is. And then this function is kind of for fun. You'll see this occasionally. All right, peek's really easy. So peek, all this one does, it's sometimes used, and it just shows the top element without removing it. All right. So those are two main functions with a for fun function. This is just sometimes used. Now, I may ask this question on the test. Is there a really easy way that we can make something peek? Just using push and pop, what do you think it would look like? Let's say I've got an int stack. Here, I'll do it as vector or template style. So say we have a stack int s. Now let's say I wanted to peek. I wanted to peek the top element of the stack. All right, so this means that I want to look at it, but I don't want to. We're not that far yet. Just realized. You guys don't know how stacks work yet, so I can't talk about that. I'm getting ahead of myself. We'll come back to it. We'll come back to it. Peek will be looking at the head, yes. Peek will be looking at the head. Once again, though, I got a little bit too ahead of myself, so let me just tell you how they work, and then I'll ask you the same question. All right, so there's two terms that we know for this. I will ask for the participation on this one. Does anyone know what FIFO means and what LIFO means? Now, FIFO applies for queues, and LIFO is for stacks. All right, what do these mean? Yeah, you guys got it. This one is first in, first out. This one is last in, first out. So that's all you have to remember. Pretty much that's it. Once you know queues and stacks, they're exactly the same thing, except there's only two differences, or one difference. The one difference is with a queue, the first one to go in will be the first one to go out, right? The first one to get in line will be the first one to be served. A stack is backwards. This one's kind of unfair. Now, when it comes to, say, computer processes, the computer processes don't have feelings, right? So they're not going to give the computer a bad 5-star rating, like a 1-star rating, to the computer because they didn't get served like fast. But stacks are kind of like unfair lines, where the last person to get in the line is the first one that's going to get out of the line. It's kind of like a stack of plates. The plate that's going to be on the very bottom of the stack is going to be, it was the first one there, right? You put down one plate, and then you start stacking other plates on top of it. And then when you're grabbing the plates, you're taking plates off the top. And so the very first plate that was in the stack is going to be the very last one to be removed. And the last plate that was put on the stack will be the first one to be removed. So that's a good example here. So I would just say maybe, for examples, line at the, line at in and out. And a good example of a stack. There's actually a few. I like the stack of plates. And also, your cell phone works like that. Whenever you're in an app or whenever you're on a website, you start clicking on the things. So what's an app that everybody has? If you think about photos, if you go into your Photos app, there's the main screen for the photos, and then you click on, say, an album, it goes into the album, and then you click on a photo and it goes to the photo. And so it's stacked. It's the main screen, album, photo, and then as you go back, you hit the back button, the photo comes off the stack, the album comes off the stack, and then you're back in the main screen. All right, so apps on iPhone or on your phone. All right, so those are good examples of stacks. We'll use stacks. All right, so let's do a quick little whiteboard. We'll start with the with the stack. This one will be the stack. All right, so I'm going to grab my little stack over here. So let's say I call, I'm going to kind of just type these here. Say it's for ints. Say I call push 3. All right. So if I push 3 into our stack, will it fit in here? Yeah, it will. We'll kind of go all the way to the bottom here. All right. This is going to be number 3. Oh, it fits in there nicely too. So there goes our 3. So say we call push again. This time it's red for some reason. So now we're going to put 4 on top of that 3. So now I'm going to ask you, if I call pop now, if I call pop right now, what element comes out first? What element comes out first? If I call pop, what element are we going to get? Remember the stack of plates. Which one went in there first and which one went in there next? Can you get the bottom stack plate? The 4 comes out, right? The 4 comes out. The 4 comes out. So say goodbye to the 4. It comes out of the stack, and now it's, you know, over here somewhere in no man's land. So say I call push again. This is kind of a just a quick highlight of how a stack works, all right? You can find all sorts of stuff like this online. If I call push on 5, we're going to put it in there. All right, and let's say I call push on 6. And then we're here. Now I call pop. Which one comes out? Just confirming. I'm just confirming. We know what's happening here. And then you're an expert on stacks. Say I call pop. Which one comes out? Six comes out. Right? So that's the last little bit here we'll talk about. All right, 6 comes out. So if I want to get to that 3, I'll have to call pop 2 more times. All right, if I want to get to that 3, I'm going to have to call pop 2 more times. I would say the best way to think about it is, let's see, I'll kind of just put them here on the side. Best way to think about it is pretend that this down here has got like, it's like walled off. It's like walled off from all society. And so nothing can, it's like, you know, it's like a very skinny hallway. And if something goes in and then something goes in after it, that line, those people are going to have to file out in the order that they kind of went in, right? No, not in the order, but the reverse order that they went in, all right? So think about like this. It's got a wall on the bottom down here. And 3 cannot get out unless 5 comes out first, all right? So a stack, remember that this is LIFO. And that's our stack example. So now I'm going to ask you one really quick question. I was getting ahead of myself here. Let's say I wanted to do a peek function for the stack, but I don't have peek. So only using pop and push, is there some way I could peek the first element on the stack? What do you think? Is there some way that I could peek the first element on the stack without, removing it? What do you think? Let's use our engineering minds. Let's use our engineering minds. Yeah, exactly. That's what I would do. Attacker, you're right. You're 100% right. We would just have to save it. So that code might look like this. That code might look like this. I could do int x is equal to s.pop, and then I can say s.push x. You okay with that one? What do you say? That makes some sense, right? We'll just pop off the top element, and then we'll push it right back in there. Now, we can't do that with a queue. We can't do that with a queue, but that's kind of that part. I may ask you something like that on the test. Say, I don't have peek for my stack, but how can I do it? That's how I do it. All right? So that is stacks. Now we'll talk about the queue. This one, you already know how this one works, so I'm just going to kind of speed through this one. We don't really need to spend too much time here. So we've got our queue. Thanks to computer science, I learned how to spell that word. And we call this one FIFO, which means first in, first out. So I am just going to confirm that you guys know what's going on here. So I'm going to call NQ on 6, and now call NQ on 5. And so here's how I like to think about this one. I like to think that this one goes in the bottom. There's no wall here, right? There's no wall. It's just a hallway this time. There's no wall here. So I like to think that 6 goes in up to the top. And then I call NQ on 5. So it does the same thing. Goes in the bottom and comes up to the top. And then I call DQ. What comes out? It's an easy question, I know, but please entertain me. Just so I can confirm that I'm speaking English. The 6 comes out, right? 6 comes out. So that one is FIFO. 6 comes out. And then, of course, if I call NQ on 4, it goes in the bottom. I call NQ on 3, goes in the bottom. All right. I guess they all kind of move up to the top here. All right, and that's it. So do we really have any questions about stacks and queues? I'll show you some of the questions I have in the review sheet, and we should be able to answer them, okay? But if you have any questions about stacks and queues, please let me know. Yeah, it's pretty straightforward. Pretty straightforward. They're just kind of backwards a little bit. So last semester, we had time to do a stacks and queues assignment. And so what I did was there was 2 restaurants. I think we had Pizza Shakes and Future Burger. I was pretending like we were in that movie WALL-E. We were in that movie WALL-E, and everyone could get their food in cupcake form. And so no one actually cared about how their food tasted. They only cared about how fast they got it. And so they would go on Yelp or whatever and review it. And they would only give a 5-star review if they got their food fast. And so we made a program that one of the restaurants used a stack and the other one used a queue. And we saw which restaurant got the best reviews. And it turns out the stack did way better because the longer someone waited, the worst review they would give. So the restaurant with the queue, which you think is fair, right? That one actually got the worst reviews. and the stack got the best reviews. But of course, that's kind of a goofy little example. In our kind of world, we have to be fair about things, so we should always kind of follow a first come, first serve. But as long as your, computer processes don't have feelings, stacks and queues can kind of be used for different purposes. It depends on how you're rating the service. All right, so that's our queue. Now we're going to move on to review. It's review time. Now, guess what? Since the time is ticking, as always, I'm going to leave it up to you to watch the review of the first half of class, all right? If you want to do that, go on YouTube and find it. Nothing about the first half of the class changes. So that review is still the same. Those answers are still there. I did kind of move them to indicate to you that if you want to go find them, you can find it in the finals folder. So let me log in here. I'll show you where this stuff is. This stuff went up yesterday, as I said. That's never what I want to do, just so you know. So if you go to test reviews, click on final, you'll see that there's the midterm review and the midterm answers there, all right? So same stuff from the first time we did a review. Now the final reviews here, of course, I'll be going over this today. I will not be writing it down in class. I will kind of just talk to you about it. And then after class today, I'll upload our answers, all right? So we're going to go ahead and get started on that now. I am going to open it up in something else because the Web Campus PDF viewer is not the best for class. But Microsoft Edge does a great job. All right, so we're going to start out. We're going to pretend like we already reviewed our classes. We're going to pretend like we already reviewed our inheritance, and we're going to pretend like we already reviewed pointers. So we're starting out at virtual functions. A few of these I'll ask for participation, but the easy ones, I'm just going to say them, kind of in an attempt to save some time. So here's the easiest one. I'm not going to ask you to tell me what this one is. What do virtual functions do? If you remember, it allows for polymorphism, right? In that an object can kind of take a different form during runtime. So if you think back to assignment 5, we had a balloon. We had a balloon pointer, and within that pointer was either a red balloon, a yellow balloon, or a blue balloon. So the virtual function will allow our program to pick out which derived class that we want. So if we're going to call the destructor or pop balloon, or get identifier, kind of any of those functions, or if you think back to the gamer code, if we're going to call receive damage, it's going to go down the chain of the inheritance, and it's going to find which object we're talking about. So I'll ask you about this one then. What 3 previous subjects have we studied this semester that are required to use virtuals? What are the 3 subjects that we studied that are required for a virtual function? I'll ask you that one. You can tell me that one. What are the 3 subjects? What are the 3 things that we need for virtuals? Ali says overloading. I would say more overriding, because we do override the functions in the derived class. But I'm looking for more classes and inheritance. So 420, yeah, those are 2 of them, right? Those are 2 of them. We need a class and we need inheritance. Now, what's the 3rd subject? What's the 3rd subject that we need? I kind of hinted at it. What was that whole deal with the grid in assignment 5? What was the whole deal with that grid? Pointers, right? That's the next thing. So in order to use virtuals, we need a class, we need inheritance, so I guess 2 classes, and we need a pointer. So now talking about pointers, I'll ask you about this one. In order to invoke virtuals properly, the derived class object must be stored in what? Where is the derived class object stored? What is it stored in? What is it stored in? Do we just put it in a regular object? Where do we put it? Where does it go? How do we make the program do the virtual part? It goes in a pointer, right? But what pointer? This goes in a pointer to the base class. The object of the derived class must be stored in a pointer to the base class. All right? So once again, I will, since I'm not writing them down, I will put all these answers in a PDF and upload it, all right? So you'll be able to reference what I say. Feel free to write them down if you're doing that, that's fine. You can tell me to slow down if I need. But the specific thing I'm looking for here is not just a pointer. A pointer is half points, but if you say a pointer to the base class, that's full points, all right? Now my face is frozen here. My OBS took a break. We lagged, I think. I think we took a little lag there. I saw my face freeze in the most attractive position. But I think we're back, all right? I think we're back here. Cool. Thank you, thank you. So I'm going to speed run these ones here, all right? Can pure virtual functions have a body? The answer is no. Pure virtual functions cannot have a body. And if you remember what those look like, a pure virtual function would be void foo is equal to 0, right? So I will kind of throw that a little bit in here. Remember that pure virtual functions, how do we do them? And do they have bodies? Well, they do not have bodies. And how do we indicate that they're pure virtual? By saying it's equal to 0. Can pure virtual destructors have a body? The answer to that is yes, they can, right? They can have a body, and if so, is the body required and why? So the body is required on a pure virtual destructor. It must have a body, and the reason for that is because the destructor of the base class always gets called, even in virtuals. There's always a destructor. So in a pure virtual function, we can indicate that maybe the base class will not have a working implementation of that function. For example, shapes. If we just have a base class shape and we call print shape, the world kind of would implode, right? That's just some general concept, right? A shape doesn't have a form necessarily. It's just an abstract class. And so if we call print shape, we'll say, well, that base class doesn't really have a function for that. But the destructor is a requirement, all right? The destructor of the base class is always called. Now I'm going to ask you this question. This was a assignment question. What's a really good reason to make a virtual destructor? All right? I guarantee you that I'll have this on the test. What is a really good reason to make a virtual destructor? I'm not interested in how the virtual destructor works. I'm more interested in what's a really good reason for it. Aside from printing a balloon popping message, what's a really good reason to have a virtual destructor? Guys, remember that? Now, yeah, I'm okay with that. 420, I'm okay with that answer when you say the derived objects have different abilities. Chatter says to make objects are destroyed in order. That's a great one, too. But the one I'm looking for most specifically is that our derived class would have a dynamic memory inside of it. Also, just so you know, I did get I guess I wouldn't call them a complaint, but I did get some discussion as part of that assignment 5 question, which was this one. And I will be going through those and reevaluating grades. So if you think you had a good answer for it and you got a 0, I may change that just a little bit. Because I do think that answers from 420 and Chowder are good answers. But the one that I really care about is if that derived class has dynamic memory in it. If the derived class has dynamic memory in it, and we do not make a virtual destructor, we're going to have memory problems. That's when Valgrind will start to cry. So that's most important that I would say about that. Right? That's most important. Now I kind of gave this one away. What is a class called if it contains a pure virtual function? It's called an abstract class, right? So that's kind of the shape I was talking about, and the print shape. If the class contains a pure virtual function, then it is abstract. Now I'll ask you this, can abstract classes be instantiated? Remember that one? Can abstract classes be instantiated? Can an object of the abstract class be instantiated? I think we've got a little bit of delay. The answer is no, right? Abstract class cannot be instantiated. So if you have a class that contains a pure virtual function, for example, shape, and we say shape equals new shape, the compiler will say this is an abstract class. You cannot have a shape object. You are not allowed. All right, so that's the answer to that one. Abstract classes cannot be instantiated. So now I'm going to ask you guys, tell me this one. What's the output of this code? I think you guys can see it pretty good. We've got a base class A, which is up here. We've got the base class A. And then we've got the derived class B. And then we've got main. So what do? I have a pointer to the base class A, and I instantiate a B into that object. I then call print1 and I call print2. You can see that both of these functions are contained within each class. So I'm asking you, what is the output of this program? What is the output of this program? This would be something that I would ask on a test. What is the output of this program? And I'll go over it for those of us who are having some struggles, but I am interested to see if you guys know. I know I'm making you do some math here, right? 72 plus 7 is 79. Negative 4 minus 60 is negative 64. So we kind of have a few choices, right? So the first option I would say is, let's see. Well, attacker kind of gave us an answer, so let's take a look-see. Attacker says negative 4 from this one. And then we see you said 79 from this one. So I'd say attacker is correct. Attacker is correct. And let's talk about it. Oh, also the goodbye B part. The goodbye B part. What about that one? Is it goodbye A or is it goodbye B? Is it goodbye A or is it goodbye B? Which one? I see 420 took a guess there. Does attacker, do you have some input on that? Is it goodbye A or is it goodbye B? From the delete. Which one do you think it is? Dan, I'm putting you on the spot here too. You say goodbye B? All right, so here is the answer. I'll type it in. We're going to be looking at a, let's see here. we're going to be looking at a -4 to start. Yeah, you're right on track there, 420, right? It's going to be -4 to start. Then it will be 79, right? Which I'm just making sure, x plus 7. And then it's going to be goodbye A. So that's the answer to this question. And this is why. So the very first thing, notice here we have an object to the base, or we have a pointer to the base class. And we instantiate an object of the derived class into the pointer for the base class. So the first thing I call is print1. So what it does is it goes up to class A. It says, where's print1? I found it. It says, is this virtual? It says, yes, it is virtual. So then it goes down until it finds what object it is. It says, all right, this is a B. And here's print1. So we're going to see -4 to start. And then we say object print2. It goes up to class A. It finds print2. It says, is this function virtual? No, it's not. So it's going to print 79 plus 72 plus 7 is 79. And then finally, we call delete object. So it goes up to class A. It finds the destructor. It says, is this destructor virtual? No, it's not. So it calls goodbye A. Do we have any questions about that? This is a type of test question that I'll ask. All right, so understand what's happening here. Which one is virtual? Which one is not? How does it affect the output of this code? All right, so that's it for virtuals. Please tell me if I need to go back, because we will be moving on to operator overloading. All right, so I'll go back if I see something, but we're going to kind of move. We're going to plow on ahead here. So, what's the first question I ask? What operators must be overloaded as members of the class? Well, there's 3 of them, right? There's 3 of those. And so we're going to see some parentheses, we're going to see some brackets, and we're going to see some assignment operator. These are the 3 operators that must be overloaded as members of the class. What operators must be overloaded as global operators? Well, there's 2 of them. They're easy to remember. You're going to see the insertion and the extraction operator. Insertion and the extraction operator. Now I'll ask what operators cannot be overloaded. Well, there's a few of them. I believe they are scope resolution, the dot operator. Let me put some commas in here. The ternary operator. I think looks like that. Yeah, it does look like that. The size of operator, and then the type ID operator. Now, before I send that in the chat, I am just going to confirm that I am right on par with that. I'm confident about all of them, except for maybe that dot operator. But I'm pretty positive. Yep. Is there 6 of them? No, there's only 5. That's what I put in the notes. There's only 5. So it's these ones. All right. Now, answer me this question. Can we define our own operators? Answer me this question. Can we define our own operators? Also, answer me this one. Why would friend functions be helpful in operator overloading? 420 attackers say no. That is the correct answer. We cannot define our own operators. Now, why are friend functions helpful in operator overloading? What do they do for us? What do they do for us? How do they make operator overloading work? Arceus, you're correct. Yes, we cannot define our own operators. And 420, you are right. Why would friend functions be helpful for operator overloading? Well, they give us access to those private members. They give us access to those private members in the class. All right? Now, you guys should hopefully remember what an operand is. The operator is the symbol. The operand are the arguments. They are the parameters passed to the operator. All right? So if I've got 3 plus 2, the operator is plus, and the operands are 3 and 2. What's the difference between the headers of the pre++ and the post++? Well, the post++ contains a dummy integer variable. Now I'll ask you, is it used for anything? I know this confused some of us before. Is the dummy integer variable used for anything? The key word in there is dummy, but I'll ask you, is that integer used for anything? Or is it just hanging out there? No, it's not, all right? I should never see you using it for something. Please do not use it. It just sits up there, right? It's just sitting up there so the compiler can tell the difference between whether or not to use the pre++ code or the post++ code. Now, this I'm going to ask you to do on your own. I will provide some answers for this, of course. But pretend you're going back to your point2D class. I want you to practice overloading the extraction operator, which will read in an X and a Y to that point2D. I want you to practice this parentheses operator. This is something we haven't done yet. Though you should know how to do it because we've done brackets and we've done assignment operators before. What does this do? It's kind of like the copy constructor and the assignment operator in that it's going to take in a point2D. It's going to change the left-hand side point2D to be a copy of the parameter. All right? So I want you to practice that one. And if you've got time, go ahead and practice a point2D plus int. So this plus operator is going to return a brand new point2D that has the integer added to each the x and the y from the left-hand side point2D. All right, so I will put my interpretation of that in the answers, but feel free to give it a shot if you'd like. So now we're going to talk about templates. Tell me if I need to go back. Of course, like I said, I will do it. So what does a template do? Well, that allows us to write generic code for a function or class that works for all types. All right, so if we make a template sort, that sort is going to be able to sort a list of any type, given that, you know, well, I'll hold off on that for now because I'd probably ask about it. But for the most part, templating a function or a class will allow us to use it for all types. So I'll ask you this one. What two keywords are interchangeable when declaring template type identifiers? Right, I call this the template type name. You know, whatever you name the template type, that's what the identifier is. What are the two keywords that are interchangeable when declaring them? It's type name and it's class. Just class. It is just class. So it's type name and class. So good job, Reckless. Can templates incorporate more than one template type? The answer for that is yes. Of course they can. So you might see something like this. Quad, which has an int and a string and an int and maybe a double. All right. That quad can have 4 different types. You have to specify them. But yes, you can incorporate more than one template type. Now I'll ask you this one. This one's a goofy one. Assuming the template type identifier is named Jimmy Neutron, fill in the following code below to initialize it to a default value. How am I going to initialize this to be a default value? What do I type here? What is the code? What do I put there to make it default? What do I put there to make it a default value? I should have had you do that in your assignment with the templates, but I don't think I did. What do I put there? It's a goofy one. I know. If I wanted to call the default constructor for that type, yes, that's exactly right. Listen to 420, that's what goes there. We say object is equal to Jimmy Neutron parentheses. All right? If it's type 1, it's type 1 parentheses. If it's T parentheses. If it's T1, it's T1 parentheses. All right? So that's what goes there. Assuming you have a single template type function void foo, how will you call it using an integer? How will you call it using an integer? The template type name is type. So these are some tricky questions. So notice that the template type name is type. So you'll notice that this function here is taking in a type, a template type already. So if we were going to call it, we could just do it like this. We might say have int x equals 3. And then we'll say foo x. That's how we call it. Now that I've given you the answer for that one, assuming you have a single template type function void foo int, how will you call it using a string? The template type name is type. So I'm going to ask you this one. Pretend I have foo. I have a string and I have foo. How will I call it so that I fill in the template type to use string? Notice that the difference here is that up here in question 5, the template type is included in our parameters. Notice in this one, the template type is not included in the parameters. So if I'm going to call foo using string, how do I do it? You can assume that, say, we've got an int x still here. That's fine. I don't mind. We'll still assume that we've got an int x here. How am I going to call this function with strings? What do you think? We're doing great here on time, so I'm going to wait for this one. I believe. Yes, that's exactly right. Thank you for your extended participation today, 420. Yes, that's how we call it. Are there any questions about that? Notice that in this one, the template type is included in the parameters. So if we pass in an int, the compiler knows what to do. It says, I'm going to call the one using ints. In this next one, the template type is not included. So that template type is hidden somewhere within the body. And say if I want to use a string with it, I'm going to have to specify it using the brackets or using the less than greater than signs. All right? So let me know if that is confusing to you. All right? All right. So I've asked this question probably 17 times. This is a question that I always ask on the test. Suppose you write a template function for sorting a list of any type. The comparison operator being used is less than. Is the function guaranteed to work for any type? And if not, what do we got to look at? What's the thing that we should consider? What will give us compiler errors? What will give us compiler errors? I'm glad it makes sense. RCS as I hoped that it would. I'm glad it makes sense. So for question 7, what is it going to work for anything? Let's say we pass an Olympic event to it. Is it going to work for anything? Or what's going to break the compiler? Will anything break it? Yes, we have to consider an operator overload. We have to consider an operator overload for the less than sign. So if you're ever in a case where you're coding your own classes and you're coding your own template functions, you're going to need an operator overload for the less than sign. Now, Arceus, I'd say you're right. In the assignment operator should also be overloaded, but only because there's a pointer in the class. If you remember our Olympic event did not have any pointers, so we don't always have to consider the assignment operator, though I'm glad you're thinking about it. And if you answer that on the test, I will still give you points. Though, the most important thing is the one that will completely break the code is the less than sign. As long as the user-defined type, class, or struct does not contain pointers, we don't have to worry about that assignment operator. But if it does have the pointers, we assume that they're going to know their rule of 3. They're going to know that they should be doing the rule of 3. And if they did it properly, we will still have no problems. All right. So I'll do this one in front of you. Let's declare a template type, a template struct called quad that has 4 different template types. Wow. That's a lot. All right, well, let's make a new file here. Let me go ahead and save it so that I can get some pretty colors. Some pretty colors on my code, please. And this will be just a quad. So I'm not going to compile this code because I know by heart that it'll work. All right, you can trust me. So say I'm going to make that quad class. What do I need? Well, I need first the template type. In here, I need a few type names. How many types did I say? Well, I think I said 4. So there's 4 of them. Now I'm going to name them T1, T2, T3, and T4. And then I'm going to go struct quad. Give it a parenthesis because it's a class. And then in here, I'm going to go T1, item 1, T2, item 2, T3, item 3, T4, item 4. And then I may ask, how do we declare this in main? Well, pretty easily, just like I showed you today already once. If we're going to declare it like a vector or anything else, we're going to have to indicate what I want every single type to be. And it comes out just like that. All right? Are there any questions about that? All right, that's how we do it. That's how we do it. We need a template there, and we need that template stuff here too. Not sure why this is not green. I'm sure the IntelliSense has a great reason for not turning my code the nice pretty colors, but I assure you that will compile. All right. So now we're moving on into recursion, then linked lists, and then stacks and queues. So we're moving along here pretty nicely. So I'm going to ask you guys for the participation here. What one thing specifically makes a function recursive? And once you answer that, can you answer what 3 things do all valid recursive functions have? So the first thing I want you to answer is what one thing makes a function recursive. The function could be bad. The function could be bad, but it's still recursive. It calls itself, right? That's what answers this part. What makes a function recursive? It calls itself. Now, that's one thing that all valid recursive functions have. It calls itself. So what are the other 2 things that would make the recursive function valid? What are the other 2 things that make the recursive function valid? What's important to have in a valid recursive function? A base case. It needs a base case. It needs a recursive call. And it needs a reduction operation. Yes, Reckless, you're right. It needs a recursive call. That's one. It needs a base case, that's 2, and it needs a reduction operation, that's 3. So I ask, what is the purpose of a base case? Well, it stops the recursion. It stops the recursion. What is the purpose of the reduction operation? To take us one step closer to the base case. The base case stops the recursion. The reduction operation takes us closer to the base case. I'll ask you this one. Can anything using iteration be done using recursion? Has something to do with Benedict Cumberbatch and inventing C++ during the Hunger Games. That's a joke, of course. But if you remember that day, I asked that question, can anything using iteration be done using recursion? I'm not going to ask you any names here. I just want to know a yes or no. And the answer is yes, yes. Thank you to Alan Turing for that. Alan Turing proved that. I'm going to remember that for the rest of my life, just so you know. That was hilarious. So, yes, anything using iteration can be done using recursion. All right? And are there programming languages that do not use loops? Yes. I'm not going to ask you what they are. Just know that there are programming languages that do not use loops at all. What does that mean? You have to know how to use recursion. R.I.P. the GOAT, Alan Turing. I agree. He was knighted, by the way. Did you know that? Little sidetrack. He was considered a criminal in I think England. He was considered a criminal for being homosexual, and then they took that off of his record, and then they knighted him. So I'm so proud of England for doing that. He's a knight. Isn't that insane? R.I.P. Alan Turing. All right, so I apologize for my sidetrack. Just have to admire the great man, the father of computer science. No, that's not how you get knighted. You get the crown for having Amazon Prime. That's what that does. If you have Amazon Prime, you get the crown. I'm not... You're kind of a jokester, so I don't know if you're pulling my leg or not, but that's funny. So, does recursion always use less RAM than loops, less memory? The answer is no. Most of the time, recursion uses more memory than loops. So, why would a programmer use recursion? And I said, because some problems are hard to think about with loops. So I'll ask you this one. And some of you may not have finished assignment 8 yet, which is fine, but is there a function that you coded this semester that would be really hard to code using loops? Did anyone try that? I know that we're kind of crammed for time, so I don't blame you, but I know some of you looked at that problem, that function. What is the function that I'm talking about? And you said, how the heck would I do that using loops? Which function was it? Which function did you code, or maybe you haven't coded it yet, but I know someone in the chat probably turned in assignment 8 already. What function was really hard to code using loops? Or maybe it's really easy and I'm just the silly one and I don't know what I'm talking about. Is that no one? All right, so I do hope, I guess, after this class, yeah, attacker, I would say, is right. That's the one I'm talking about. Now, maybe you're a genius where we had to destroy the lands, yeah. Maybe I'm not a genius and you are, and you looked at that and you said, oh, I could code that using loops. But I'm not that person, all right? So count square miles. Also, if you, well, I'll leave that for after that's due, but That function is, I think, really hard to code using a loop. You can try it. I think you'll have like 10 if statements. But count square miles, I think, should only be exclusively done using recursion. It makes that function probably 20 lines less or more. It's very easy to do using recursion. Yeah, the recursion code for that is very cool. Another function that I'll talk about, just so you know, I won't ask you about this on the test. I just want you to know that I came across this in my life. Say you're given just a string of characters, and I ask you to generate every combination of those strings. So if I give you maybe like an X, a Y, and a Z, I would want to see X, Y, Z. I would want to see X, X, Z, Y. I would want to see Y, X, Z. I would want to see Y, Z, X. And I would want to see Z, X, Y. And I'd want to see Z, Y, X. So those are all the, I guess, man, I'm your instructor, and I'm failing to understand combinations, permutations right now, so I'm going to use one word. Don't get mad at me if I get it wrong, but those are all the combinations of those three letters. If I asked you to write a function to do that, I guarantee you the recursive implementation of that is way easier than the loop implementation of that. If you tried to do that using loops, best of luck to you is what I'd say. The recursive version of that is much easier than the loop version. So there's quite a few of those in the world. That's all I'm trying to say. You'll have to know how to use recursion, and it's really cool. It's really cool. So this one, I need to fix my wording from that day. I was going back in my notes, and I kind of corrected it before I uploaded it. But I'll ask you, when solving a problem recursively, what's the first thing that you should try to do? I would say is try to simplify the problem into little building blocks. To break down the problem to the most simple form, what's the least amount of work you can do in one function call? And so if you're talking about count square miles, the least amount of work you can do is to look at 1 square mile and count it or not. That's the very smallest little building block in that problem. If you try to look at the whole island and you go, all right, I'm going to make a snake go around it and count it and mark it, you're not thinking about it simply. So when I ask that question, what's the first thing you should do when solving something recursively? Try to break it down to its most simple form. Break it down to the base case in the recursive case. Figure out what that is. All right, so I'll let you answer this one. Look at the recursive function. What tree does it make? What tree does this function make? I'll zoom in on it for you. It's a little tiny. What tree does it make? And by the way, this is an equal up here. It's kind of hard to see, but there's equal there. Binary tree, that's correct, all right? It's a binary tree. And how do we answer that question? Or two-ary, if you'd prefer. Two-ary, I'm fine with that. How do we determine that? What is the most amount of times that this function calls itself in one go? And that is the second else if here. It's this one. It calls itself twice here. These are guaranteed to execute not maybe at the same time, but one right after the other. So this function is a binary tree. Binary tree. Calls itself twice at most. At most. Now, here's a little puzzle for you guys. Can I pass any number to this function? Or is there a number that I would pass to this function that would make the program run infinitely? This is something good. This is a good practice question, all right? And I'm sure there may be a few examples, but can you give me one example of a number that if passed to this function, it will run forever? Is this function clean? Is it perfect? I can pass any integer in it that I want? Or is there one example at least of a number that if I pass to it, it will run endlessly? And attacker is right. Attacker got it. I'm sure there's more. It might be the odd negative numbers or just an odd number in general. But what happens here if I pass -1? Well, we'll say x is less than 0. So it calls this one. And -1 plus 1 is 0, so it comes up here and returns. But then the next time it calls itself, it says -1 plus 1 is, or -1 plus 2 is 1. So it calls foo at 1, comes back up here, x is not equal to 0, x is not less than 0. So then it returns this recursive call, which is 1 minus 2, you're back to -1. So it goes 1, -1, 1, -1, 1, -1 into oblivion. All right, so understanding that is very important. Do you understand how this recursive function works? And by just looking at it, can you tell which numbers would break it? And -1 is a great example of that. All right. So let me know if you've got questions about that. And yeah, that question's there. So I recalled that. So now we're going to move into linked lists. So once again, just let me know if I need to go back. We'll kind of speed run this stuff. I think I took out one. Yeah, okay. So we just talked about this. It should be fresh in your mind. So for the most part, I'll be speed running it. But what's the difference between a singly linked list and the doubly linked list? And I ask you to practice coding the node structs. So all I mean by that is if you've got a struct SLL node, you've got the data, for example. Now, if it's a template, it's a template, but maybe this just stores integers. So you've got an int data, and then you've got an SLL node pointer to the next node. And then if you make a DLL, what's the difference? Well, it's pretty much the exact same thing, except it has a next pointer and it has a previous pointer. All right. So that's probably the extent I'll ask you about DLLs. Like I said, I'm not going to make you code deleting a DLL, though it would be the same. I'm not going to make you code inserting to DLLs or anything like that. Any coding question about linked lists, I'll ask only about the SLL. But I will kind of ask questions like this. What's the difference between an SLL and a DLL? The DLL points both to the next node and the node that was previous to it. What is a circular linked list? Well, circular linked list is any linked list where the last node points to the first node, makes a circle. If the list is non-circular, where does the ending node point to? And also, if the DLL is non-circular, where does the head node point to previously? What's the answer for that? So if this is the ending node, where does next point to? And if this is the very beginning node, where does previous point to? What's the answer to that? If it's a non-circular. The null. It points to null, right? Points to null. This will point to null, and the previous will also point to null. All right, so when I ask you, say, find the ending node in a singly linked list, you're going to look for the null. You're going to look for the null. All right, tell me what this one is. Of the 4 types of linked lists, which ones, of the 4 types of linked lists, which ones require a pointer to always look at the head of the list? Of the 4 types of LLs, singly linked list, doubly linked list, and then their circular counterparts. Which one or ones require a pointer to always look at the head of the list? We talked about that. That is correct. Attacker is correct. It's only the non-circular SLL. A non-circular DLL has the previous pointer. So if you think about it like that, 420 on a DLL can be traversed in two directions. You can go backwards on it and you can go forwards on it. So if you have a head node that's pointing to, say, the tail on a DLL, you can actually backtrack your way up to the head. So the answer to that is there's only one linked list that requires a pointer to always look at the head, and it's a non-circular singly linked list. The DLL can be traversed in two directions. Why can it be traversed in two directions? Well, the answer to that is because you have the previous here, right? So you can always go backwards on it. You can always go backwards. What are the three ways? I'm going to change this to just two because one of them is not valid. But what are the two ways to swap nodes in a linked list? So the two ways are you can either swap the data within the nodes, or you can change up the links, right? So remember that example of the train. The example of the train. Would you rather just swap the carts, or would you rather take out all the sandbags and then put them in the opposing train? The opposing cart, right? So I'm going to change this to just two, because the third way is possible, but it's definitely not valid. And so then I ask, if the node contains over 1 gigabyte, what is the best way to swap? It's to change the links. So you're going to end up typing that most disgusting swap function that we typed up yesterday. But guess what? It will be much more efficient than trying to transfer sandbags from one cart to the next. All right? When inserting a node to an SLL, how many pointer updates are required? And I'll ask this question. You guys can answer these two. When inserting a node to an SLL, how many pointer updates are required? Also, when swapping nodes in an SLL, how many pointer updates are required? Is it the same for nodes that are adjacent and nodes that are not adjacent? So we're kind of answering three questions all at once here. Let's start with the insert. When inserting a node to an SLL, how many pointers do we have to update? How many pointers? This one's for all the bucks. What is it? How many pointers do we update? Visualize it. Visualize that little image that we had. And there's a node floating up into the linked list. How many pointers have to change? Which ones are we updating? Two. 2 pointer updates is correct. If we're going to insert a node to an SLL, how many pointer updates are required? The first one will be the node previous to it. So that might be the head node. That might be the head pointer. That could be the ending node, right? So we're going to have to update the one that's previous to it. Even if there's nothing previous to it, we'll still have to update the head. And then we also have to update its next pointer. So for that brand new node that's going to come into the list, it's got its next pointer. And where are we going to send that pointing to? We're going to send it pointing to the next node. So there's 2 pointer updates. And then when swapping nodes, I guess I gave you some time for this. But this one's a little tricky. Pretend it's just adjacent nodes. Do you remember the answer to that? If we're just swapping... all right, attacker's on top of it. Yeah, I didn't have to assume anything there. Right, so how many pointers do we have to update in a singly linked list? If we're swapping nodes that are adjacent, only 3. It's the left, the right, and the left previous. And if they're not adjacent, we have to change the left previous, the right, and the right previous. All right? So I'll ask you to practice this. Write the code to insert a node at the end of an SLL. Assume that the head is passed into the function. So what do I mean by that? If I ask you to write the code for that, I'm going to ask you to do this. I'm going to say, hey, void insert SLL, whatever you want to name it, and assume that the head is passed into the function. So that just means this. Something like that. Maybe even this, head, if you'd like. So then I ask you to write the code for that. Well, we could do it iteratively, right? If you want to do it that way, let me do it this way. Sorry. We're going to want to insert to the head and also the item, right? Also the item. at the end, right? So let me kind of reread that again. Write the code to insert a node at the end of an SLL. Assume the head is passed into the function. Also assume the item would be passed to the function too. So we could do it iteratively. I've done that before. Let's do it recursively. If head next equals null pointer. So we asked how many pointer updates do we have to do if we're inserting. Here's pointer update 1. What's the next one? This is the second pointer update. All right. So if the head next, this probably will make you guys mad. So I'm going to change it to node. Right, and just assume that if we call it, it's going to be called like this. Insert SLL. You'll pass in the head like that. And then you'll pass in, say, 3. So pretend that it's called like that. All right? And so I'm going to say, if the node next is null pointer, we're at the end of the list. So I'm going to allocate my node. I'm going to insert the data, and I'm going to update the next pointer. Else, we're not at the end of the list, so I'm just going to call insert SLL. What do you think the reduction operation is here? I'm definitely going to pass in the item, but what's the reduction operation? Take a guess. What do you guys think? What do you think is the reduction operation? Up here is the base case, right? Up here's the base case. Yeah, I need to be better about my comments. I need to be better about my comments. I tried to put a ton of comments in my code yesterday. Attacker, you're right. That's the reduction operation. This is the recursive call plus reduction. That's how we insert nodes recursively. That is a recursive insert on a linked list. Look at that, folks. Isn't that crazy? Isn't that amazing? Isn't that amazing? Means here, down here, we're not at the end of the list. Keep going. So we'll pass node next to it, and then up here we'll check if node next, this is node next, right? If node next is equal to null pointer, then so on and so forth, all right? So that's kind of what I'm asking you there. I'll be sure to make some updates to that. And then I ask you write the code to deallocate a linked list. I did both of those for you in class already. Assume the head is passed into the function. All right. So we're now at the end here. What is FIFO and LIFO? You guys know what that is. We talked about it. First in, first out. Last in, first out. Stacks are LIFO. Queues are FIFO. What is a real-world example of a stack? Plates at a restaurant. What is a real-world example of a queue? The line at In-N-Out. What does pop or dequeue do? It takes out the top element. What does push or enqueue do? It puts an element inside of the list. Last question. What is the output of this code? What is the output of it? What do you guys think? Take a look. What is the output of that code? What is the output of that code? Let's see. This one's kind of hard. You definitely want to write something down, right? I'm going to do a snipping tool. If you get to the answer before I do, please put it in the chat. So excuse my really terrible handwriting with the mouse, but let's see. We in Q76. Where's my mouse? We in Q76 here. then 42 is next in line. The -1 is next in line. Attacker says 22. We'll see. And then we put 22 in line. So if we call DQ, the 76 pops off. This is 76. And we call DQ again. That's going to be 42. And then we push onto the stack another DQ. So we push on -1. And then we push on another DQ. So that's 22. And then we push on G, which is 76. And then we pop off 76. And then we pop off the 22. Did you follow that? You're going to want to practice with that one, I think. All right. But that's a stack and a queue. Working together. Melting your brain. Melting your brain. So this answer is 22. All right, and that wraps up our stuff. That wraps up our stuff. That's it. That's it for everything. That's our whole class, folks. This is the end. No more brain melting, except maybe this weekend when you're working on that linked list assignment. But guess what? I gave you most of the code for that, so you can't even be mad. Can't even be mad at me. You'll still have to do the work, obviously, but like I said, I kind of gave you most of the code for that. So don't get mad at me. I'm trying to help you. All right. So I guess now it's time for my. Yeah, I'll do that one for you. I was this close to banning you, by the way. I was this close to banning you. And then I saw C++ and I said, what? What is that? I was this close. My finger was on the mouse. I was this close to banning you. Do I have big followers yet? All right, guys. So, just going to remind everybody. I'm going to remind everybody. Tomorrow we have the test, all right? I said this. I know that you guys are working on a lot of stuff right now. So I am not going to make the test from Hades, all right? I'm not going to make that test. It will not be easy. It won't be a walk in the park, maybe for some of you. But it won't be the test from Hades. It won't be that bad, all right? I've given you the review. You should be on top of it, all right? As long as you look at that review at least once and you have it with you, you should be able to survive. All right? Don't forget to keep up with those assignments, all right? Just, get your assignment 8 in, get your assignment 9 in. I'll grade it. Yes, the test will be curved. As you see, last time the test was not curved very much because there are some smarty pantses in the class. That's how the curve works. But if I somehow make the test ridiculously hard and the highest score is a 75, you guys are all going to get like 25 extra points, all right? So please don't let that motivate you to do bad on purpose. Do your best, all right? And if I see an obvious reason, if I see some obvious stuff in there that I didn't cover, it didn't sink quite in, you will be curved, I promise, all right? I promise. That will happen. I'm not saying the curve will happen, but I'm saying it might happen. Do your assignments. I'm here. You can message me if you want. I had a great time these 5 weeks. I know I was disorganized at times. So I appreciate you guys hanging with me, joining me on this C++ journey. I had a great time talking to all of you. I do love when you come to office hours. I met so many cool people this semester, and I'll miss you all. I'm going to tell you this. I am a giant, all right? I'm 6'7". So if we're all on campus again someday and you see me on campus, you see the giant man with the glasses in the engineering building, that's me. You can come say hi if you want. All right? I'm a giant person. You can't miss me. So I've had students, I was getting my COVID shot the other day, and I met I met Cherry, and I met a student I had last class. So I love when you guys come say hello. You can't miss me. Please say hi if you'd like. I had a great time once again. Thanks for taking my class. I hope you learned something. And I'll be here this weekend if you need to chat. All right. I'm glad that you thought it was a great class, Megan. Thank you for all your fun jokes. You were a pleasure to have in class. Attacker, it was so nice to have you in class. RC, it was so nice to have you in class. Allie, it was so nice to have you. Flyer, it was so nice to have you. Reckless, you're making me blush. It was so nice to have you in this class. You are all so welcome. Thank you for being in my class this year. Say good things about me. Let the freshmen know. Thank you, Sarah. I'm so happy to have you in this class. 420, it was so nice to have you in this class. Thank you. I'm glad. I hope that it was followable. I hope we learned something. I hope C++ is not the scariest thing in the world anymore. All right? Hopefully we'll all be masters someday. I hope you guys have a great rest of your summer. Come say hi if you want. Reckless, I am a graduate student, so I go wherever they throw me. All right? So they may throw me in 302. Maybe you can send me an email, and I'll update you on my assignments. All right? So wherever my advisor puts me, that's where I go. So I don't really have a choice, but if you send me your email, I'll put you on my update list. And if they ever throw me in 302 sometime in the next semester, I will let you know, okay? You make me so happy to see you maybe want to take my class again. Thank you, Chowder. It was so nice to have you in this class. I hope you have a great summer. All right, you're all free to go. Message me if you need. I will help you. I will help you with the stuff. I might even do some voice calls, okay? I might do some voice calls. So if you need me, let me know. I will see you all guys later, hopefully. And those are my final words. I love you all. You were great. Goodbye.